Now, there are a few factors which affect the corrosion rate. So let us take the example of the active passive metal itself and see how the different factors will change the way in which the cathodic reactions will occur. Now, let's take the example of a pipe which has going into different terrains. Now here you have a certain velocity. When it goes down the slope, the velocity will be high. When it goes up the slope, the velocity will be low. And here the velocity will come back to the original pace once again. Now, when the velocity is normal, then we can say that the cathodic reaction formation or the cathodic branch intersects the active region somewhere over here. So the corrosion current density is at this point. Now if suppose you have the lower part, in this case the velocity is going to be high, so more and more oxygen will interact with the pipeline walls, and at this point the cathodic branch can intersect either here or here and as well as here. So at each of these points the corrosion current density is going to be higher. If it is at this point, it is in the active region, so the corrosion current density is going to be definitely very high. Let us assume that this is of carbon steel and not of stainless steel, and let's ignore this part for now, and I'll come back to it in a few minutes. So in the third case, when you have a velocity which is low, not enough oxygen is going to reach the parts, so the cathodic branches will intersect in at a lower potential, so your corrosion current density is over here. Now this means that the corrosion current density in each of these parts is going to be different, so you cannot really use the same MPY or MMPY to calculate the life of the entire pipeline. Although it is difficult, and you may have to see that each part is at least it is mentioned that each of these parts will have these kind of different corrosion current densities and corrosion rates as well. Now let us assume that this is a stainless steel pipeline for now. Then in case of stainless steel pipeline, let's just erase these two parts and take into account the green region only. So in the green region, you have the velocity increasing. In this case, if the velocity intersects in the passive region, then the passive film formation is going to occur. So the current density will remain constant at whatever point the a passive current density is already present. If you have active region, then you will have a higher corrosion current density, as I mentioned before. If you have it intersecting over here, then the situation is the worst, because sometimes it will act as passive, sometimes it will act as active. So in this case, you will not have a freely corroding surface. You will have passive film formation and then active corrosion. Then you will have passive film formation and active corrosion. So this half formed passive film will actually increase this corrosion to a much higher extent, and this particular region is really dangerous. So if your pipeline consists of active passive metals, I would really suggest that you please do this kind of measurements and see where it actually intersects with the where the cathodic part intersects with the active passive region. That would probably give you a better idea of why your pipeline is corroding or where it might corrode in future. So that's how the velocity can be quantified. Now, if we suppose take the example for concentration. Now, in concentration, you have, let's say that the pipeline is half above ground in the sand and it is immersed in the sea water. So if it is in the sand, then in this region you have a fixed chloride, sodium chloride, that is relevant to the sand. If it is in the sodium chloride, if it is in the sea, then it is going to be have 3.58%. In this region, which is the splash zone, you are going to have a high chloride medium sometimes and a low chloride medium sometimes, depending on where the splashing will occur. So if you have a lower chloride medium, your now we are not really going to consider all the hydroxide reactions. We will now try to consider the chloride reactions. So the chloride reaction cathodic part will intersect over here in this case because of the sand. In seawater, because it is 3.5, it can intersect over here. In this case, because it is splash zone, sometimes it may go up and sometimes it may come down. So that's why here you can have more corrosion products sometimes and less corrosion at other times, but the original corrosion products that have been formed at the higher corrosion current density will continue to grow. That's why the splash zone will have the highest corrosion that is seen in a particular pipeline. Obviously, the lower corrosion will have the lower corrosion current density because we have the chloride ions in a lower content. So if there are only two chloride ions, they will interact with only two Fe ions. If in soil, in the seawater, we have 10 chloride ions, they will intersect with 10 Fe ions. So that's why in sea you will have a higher corrosion current density as compared to the sand. So with respect to concentration, we have to consider the different ways in which the same pipeline steel can corrode. Even in case of pipeline which is not really in the marine environment, but say it is near a river. Even in near the river, what happens is the soil, the chloride content here is going to be different, the here it's going to be different, and at the region far away it's going to be different. So for each of these parts, if you put the same pipeline and you calculate only 1 mmPy quantity, it is not going to actually match each of these three sections. So it is likely that you will find corrosion happening in some parts. So it's necessary to look at the concentration in a quantitative manner as given here. The next section is of ionic types. Now ionic types is, for example, here you have majorly oxygen and moisture. In this case you have chlorides or you have sulfates. So when you have different chlorides, as if you remember in the example that I showed previously, you will have different cathodic reactions. So for a water and hydrogen you will have a certain cathodic reaction. For chlorides you will have certain cathodic reaction. For say sulfates you will have a different cathodic reaction. So for each of these parts you will end up having a different corrosion current density, and here you will have a corrosion current density that will be relevant to the one that is highest, so somewhere around here. And for the one that is not exposed to the other ions but only to one, you will have a lower corrosion current density. So if you are people who already work in this field, you will realize that the parts in under the soil, the pipe parts are actually coated with very different materials and coatings as compared to the coatings that are given on top, because especially that is because of this difference in the corrosion current densities for the same pipe steel. So this is how the ionic types can be quantified. The next factor of temperature. So temperature is important in two ways: temperature with respect to what is flowing inside the pipe and also the environmental temperature. So if suppose the temperature inside is very high, say in and around noon, then that high temperature can lead to higher corrosion. So say somewhere around here. If the temperature is at night, then it can be low, so the corrosion can occur at a lower way. So the reason why temperature plays a role is when you have higher temperature, the oxygen ions that are present are more active, so they will go, they can, their vibrations will be more. So that's why the interaction between the oxygen ions or the diffusion of the ions inside the soil will also be faster, and the interaction of the corrosion will occur faster. So that's why you will have a higher corrosion current density. If it is colder, then the diffusion or the interaction will be slower. So when we want to plan for pipeline corrosion, pipeline installation, or such kind of above ground storage installations, it is prudent to try and understand what are the possible highest temperature parameters that are possible, and not just only the internal temperatures, the environmental temperatures as well, because the external temperature will also start external corrosion, and you, if the internal corrosion also starts, the pipelines will start leaking very quickly. So you have to take into account both the cases and go for the highest corrosion current density when you're planning the thickness of the pipeline. Next is the crystal structure. So now crystal structure is really important when you have stainless steels, because stainless steels have the problem of sensitization or chloride mediums. Also, in other types of steels or alloys, pipelines, steels as well, you have something called the grain boundaries. So grain boundaries are those regions which are most susceptible to corrosion. For example, in grain boundaries are basically like pavements. So grains are like pavement. So you have a pavement which goes straight, and you have another person who has started putting the pavement in a straight slant fashion. So when these two intersect, this part is the most susceptible to breakage, and if say you have rainfall, then the rainfall will go into these cracks and push out the pavements. This is exactly similar to what happens in grain boundaries. The grain boundaries are high energy states, and if they come in contact with oxygen or moisture, they will interact and start corrosion first. So when you have higher grain boundaries, the corrosion the corrosion of the pipeline will be higher. So now this crystal structure is not really related to the different cathodic regions, it is actually related to the different anodic regions. So you will have a single cathodic branch of say oxygen and water. If you have higher grain boundaries, you have a certain you have a certain say anodic branch. If you then do some kind of heat treatment which leads to lower grain boundaries, then your anodic branch is going to change, and the corrosion current density will also now change. So here the difference comes in what is actually going to be what is actually going to be affected. It is not the anode cathodic branch, it is actually the anodic branch which will lead to reduction or increase in the corrosion current density. The next factor of pH. So pH is important when you have different materials in this in the form of cathodic species, or you have cathodic protection applied. Then then in that case, the H plus or H plus concentration is going to be different. So H plus concentration being different will affect how your pipeline steel will corrode. Now let's take a look at the pore bay diagram. Pore bay diagram is the plot between potential and pH. Now, if you take the example of carbon steel, then carbon steel at 7 pH has point is 7 is somewhere around here. So that is in this case in Fe2H plus. So it in presence of acidic environment, Fe will undergo corrosion. So basically we can take this and put it take the H2 formation cathodic reaction and say that the corrosion current density is going to be somewhere over here. Now if you say that the pH has now increased, then the pH increased means that the at 13 pH, if we plot it, Then in here, in on the same H2 plot, it is in the Fe3O4 region. So for a higher pH, it is not going to form Fe. It will actually form Fe3O4. So the reaction product that is going to be formed is different, and the corrosion current density or the corrosion rate may also be affected similarly. If we assume the formation of water or hydrogen, then the product formed will be Fe2O3 in a higher pH. In a lower pH also, actually Fe2O3 will be formed. So with respect to the cathodic reaction also, you will have different corrosion products, and the difference in corrosion products affects the pipelines because these will not dissolve in the water or the pipeline water if it is present. So these will remain as particles in the pipeline and will affect the flow that is present. So if you have some sedimentation of corrosion products, it is a good practice to look at the pore bay diagram and the pH that may have changed locally. So you do not really need to pH to change during the entire pipeline. It can change only in this place and it can recover in the other place. So the corrosion can occur here differently than what it occurs over here. So that's why it is good practice to refer to the pore bay diagram as well.